In this lesson, we're going to be graphing polynomial functions from factored form. So this is a very big idea for this unit, and I would argue that this idea is very similar to something you did in grade 10, because in grade 10 you graphed quadratics in factored form. So in grade 12 we're just graphing any polynomial function from factored form. So it could be cubic, quartic, quintic, so forth and so on. Okay, so we're going to learn several ways to do it, and hopefully you find one of them to be appealing to you. Okay, so let's do some review first. So something that you should be very comfortable with when it comes to factored form. So given the function f of x equals x times x minus 3 times x plus 2 times x plus 1, how can we determine what the x-intercepts are? State them. So because it's in factored form, finding the x-intercepts is pretty easy. You let f of x equal 0, okay, and solve. And like I said, it's pretty easy to solve this equation when f of x equals 0 because we're in factored form already, right? So you can apply the zero product property. So if any of the factors are 0, then the product will be 0, and that will make f of x equals 0. So the x-intercepts will be 0, 3, negative 2, and negative 1. So 0, 3, negative 2, and negative 1. So this graph, even though we might not know how exactly the graph looks like, we know that there are 4 x-intercepts. All right, how can we double check that the numbers above are in fact the x-intercepts of the polynomial function? Well, algebraically, we just need to verify that these are the zeros of the polynomial. What does it mean to be a zero of a polynomial? That means at this input value, at this value of x, y or f of x is equal to 0. So let's check if they are zeros. Check that f of 0, f of 3, f of negative 2, and f of negative 1 are all equal to 0. Okay. And by looking at the function, how can you determine what the degree is? And I meant to say the equation, okay? So if I look at the equation here of f of x, how do I know what the degree is? Well, you can actually do this pretty easily. You can think back to what you did in grade 10 once again. So look at here, I have f of x equals x plus 3 times x plus 1. Well, what's the degree? Hopefully you can say a degree is 2 because you have 2 linear factors multiplying to each other. And hopefully you see when you multiply these two, you'll get x squared something something something. Okay, but what matters to you is you can see the x squared that you're going to generate when you expand and simplify. Now for this function though, you don't have 2 linear factors, you have 1, 2, 3, 4. So I don't want you to expand it, but I'm hoping that you can see when you do expand it, you're going to get a quartic because there's going to be an x to the power of 4 term. Okay, so how can we determine what the degree is? Can you determine the degree? And if yes, explain how. So yes, we can by counting the number of linear factors. Okay. How can you find the y-intercept of the function? So this can be applied to any function. So evaluate f of 0. Okay, when x equals 0, what is y? So we've been saying that forever, so hopefully everything we've said so far is pretty straightforward. Okay, this is just a quick refresher that to show you that factored form is really useful for one thing. It gives you the zeros of the polynomial function. It gives it to you right away. You just have to look at the factors and bam, you know what the zeros are. You don't have to guess around. You don't have to solve for them. And you can also determine the degree by counting the number of factors. So we're going to put these ideas together and try to help us graph a polynomial function. Okay, so I really want to graph f of x. So what I've done is I helped you by plotting the 4 x-intercepts. And what I'm going to do is I'm going to use these x-intercepts and I'm going to split the graph into intervals. Okay, I'm going to split it into 5 intervals because there are 4 x-intercepts. So I will have 5 intervals. The first interval here is when x is less than -2. And the second interval when x is between -2 and 1. And then -1 to 0, 1 to 3, greater than 3. So you have 5 intervals. So let's look at the very first interval when x is less than -2. I'm going to say something, and hopefully we can all agree, that one of 2 things can happen on this interval when x is less than -2. The function can be positive, or the function can be negative. Now what cannot happen is the function is both positive and negative over this interval. Okay, so why can this not occur? Why can't the function be positive and negative over this interval? Because if you want it to be positive and negative, you will introduce another x-intercept. And we can't introduce another x-intercept. We already know that this function has 4 x-intercepts and we've plotted already. Okay, we can't introduce a 5th x-intercept. So because that is the case, it can't look like this. It can't be positive and negative simultaneously. It must strictly be positive over this interval or negative over this interval. Okay, we're going to figure out which one, but that's a very important idea. In fact, we can say the same thing for the other 4 intervals. It could be positive or negative for any of these intervals. Okay, so you know what? Let's say it's positive, and then let's say it's negative. That's a possibility. Okay, I'm not saying that's the correct graph. I'm just saying that that's a possibility of the correct graph. So on the first interval, it could be negative, and the second is positive, third is negative, fourth is positive, and fifth is negative. Once again, I'm not saying it's the correct graph. I'm just saying on each interval, it has to be positive or negative. It cannot be positive and negative. But you know what? I have a sneaky feeling that I'm wrong here. So how can I verify that the function is positive or negative on each given interval? So what we can do is create what is called an interval table. So as you can tell here, I have a beautiful table where the intervals that we had on the previous page are written out. And then my job is to fill in the interval table. I have to find out whether the function is positive or negative at each of these intervals, which was the question we had previously anyways. So how do we do that? So you use these test values on these intervals. So what's in this interval of less than -2? Well, infinite numbers. You can do -2.5, -3, -4, -5, anything less than -2. So I chose to use -3 as my test value. And I found out that f of x was 36. Oh, sorry, f of -3 was 36. Who cares it's 36? I just care the fact that it's positive. And on next interval, it's negative, and then positive, and negative, and positive. And when I take a closer look at this interval table, I'm feeling very confident. This gives me really good vibes. So I said this is good because this was a quartic. This is a quartic with a positive leading coefficient. Okay, quartic with positive leading coefficient. So end behavior must be quadrant 2 to quadrant 1. And if it's quadrant 2 to quadrant 1, this is giving me good vibes. The end behavior is correct. Plus and plus. If I did not see plus and plus, then I know I was wrong. So that's why when I saw my previous graph on the other page, I know it was wrong. Like there's no way the graph can look like this because the end behavior is wrong. Okay, so what we're going to do is now graph this. So it's positive on this interval, then negative, then positive, and negative again. Oops, and then positive. That was not pretty. Let's try that again. Okay, there we go. So whenever I do these questions, I have 2 questions from students. The first one, they always ask me, how low do I go? Oops, how low do I go? Because you can make it a lot lower than what I have here. And my answer is, we have no clue how low we go or how high we go. To find out the answer to that question, you need to take calculus. But in this course, we have no interest in finding out where the function is turning, so we don't care about the local max or min points. We just, draw what looks to be correct, and as long as the intervals of where it's positive and negative are correct, we're going to accept the graph. But I will say this, don't go crazy and try to make it go really low because you're just making it really hard on yourself. The second question I get, or second thing that students say to me, is that they assume that the local max point occurs halfway between the x-intercepts. So local max and min points will occur, for example, here at -0.5 and -1.5. But that is incorrect. That kind of logic is flawed because you're thinking about quadratics and where you average the zeros, you find the axis symmetry and all that good stuff. But that does not apply to other degree of polynomials. So please don't assume that the local min or local max points occur halfway between the x-intercepts. So don't try to average the x-intercepts or the zeros. It just doesn't work out. Okay, so hopefully that clarifies the 2 very common misconceptions that students have. But this graph is really bothering me. It just does not look pretty. Sorry. I'm going to try one more time. It's just not looking nice. Beautiful. That's a little bit better. You know what? That's bothering me too. Sorry. So since I'm fixing it, I have 2 more comments I want to make. When you graph a polynomial function, you should think of the words smooth, round, and continuous. Those are the 3 words that are going through your head when you graph a polynomial function. So it's going to seem nice and smooth, and it's rounded corners, and continuous. Technically, if you graph a polynomial function, you never have to lift up your pencil. Okay, and the one thing that students have a very common mistake with is the end behavior. They always have a tendency to draw their polynomials and end it up like a straight line. I don't want to ruin the graph, but I know I'll show it. They like to do this. Okay, they make it very straight at the end. I have no idea why, but like 80% of the students do that. Please don't make it straight, okay? Because you know the end behavior. This behaves like a quartic, okay? Numbers don't behave linearly as x becomes very large. That would be very strange. So please don't change it to a line, okay? Keep it as a quartic. Okay, so let's graph a cubic together. So what I'm going to do is I'm going to write the zeros. So -1, 2, and -3. So if these are the zeros, I'm going to rearrange them in the right order. So -infinity to -3, that's my first interval, so less than -3, and then between -3 and -1, between -1 and 2, between 2 and infinity, so anything greater than 2, which makes sense. 4 zeros, 3 intervals. Okay, now I'm going to use test values. So you can use any number less than -3. You can use any number between -3 and -1, between -1 and 2, greater than 2. So you can do that. I'll give you some time and you can calculate that, but I will just fill in the table because I don't know what test values you're going to choose. So let me just do the calculation. If this was negative, you get negative. Okay, so you can use your test values and hopefully we match up. And I actually cheated a little. I didn't use test values, I just thought of something, but I'll teach you what I'm thinking of in a few minutes. So let's use the zeros and plot the corresponding x-intercepts. Okay. If you want, you can add the y-intercept. F of 0 is -6, so the y-intercept is -6. So here we go. That is your cubic. So we use an interval table. Well, first we use the zeros to create the intervals, use the test values to fill the interval table, and now that you know when is it positive, when is it negative, you can graph the function. Okay, remember, on those intervals, it cannot be simultaneously positive and negative because that will require you to introduce another x-intercept, and I added a y-intercept for good measure. Okay, so the problem with this method is that it's kind of tedious. Okay, there's a much faster way to do it, so let's investigate. Because I don't want to use test values, I don't want to make an interval table if I can get away without doing that. So what we're going to talk about is the order of the zero. Okay, so first we're going to ask ourselves what's the degree of these following polynomials. This one, hopefully you can say, is degree 3. This is degree 2. This is degree 4. And this is degree 3. So hopefully you notice that for part C, we have, and part B, these two factors, x minus 3 and x minus 5, they were repeated twice. Okay, now because they are repeated twice, we say that the 0, okay, has an order of 2. So 3 is a 0 for g of x, but has an order of 2 because the factor is repeated. Okay, and for D, we say that the 0, 1, okay, 1 is a 0, and that 0 has an order of 3 because the factor was repeated 3 times. Now, why do we care about the order of the 0? Because the order of the 0 has a huge impact on the graph of the polynomial, and that's what we're going to use to help us generate a shortcut for graphing polynomial functions. So using the order of the 0, which can be determined by seeing how many times we repeated, if at all, that factor from the factored form, then we can tell the order. And I'll show you an animation on the order of zeros, and then we'll come back to this. Function f of x right now, the equation is written here and the graph is here. So I have 2 zeros, and you can tell from the graph we have 2 x-intercepts. So the 2 zeros are 2 and -3. So the exponents, right now, a is equal to 2 and b is equal to 1. And those will tell you the orders of the 0. So the 0, 2 has an order of 2, and the 0 of -3 has an order of 1. So what I'm going to do is I'm going to change the order of the zeros and hopefully can see what happens to the graph. So first thing we're going to do is change A. A is 2 right now. And when I press this button, change A, it's going to change the order from 2 to 4 and then to 6. And what I want you to do is focus on the graph, focus on the x-intercept here. And I want you to see that regardless of what the order of the 0 is, whether it's 2, 4, or 6, I want you to focus on the behavior of the graph here. Let's do it. Okay, let's look at it one more time. Okay, so hopefully you can look at the video again if you didn't get enough of it. The sign of the function did not change. Okay, when the order of the zero is even, whether it's 2, 4, 6, and in fact you can make it any even order. So 2, 4, 6, 8, 10, so forth and so on. You'll see that the sign of the function does not change. It goes positive, and as you pass it, it will stay positive. Okay. Now, if the order of the zero is odd, then guess what? It will change sign. It goes from negative to positive, or it can go from positive to negative. But in this example, what we have is negative to positive. So I'm going to change b. Right now it's an order of 1, and I'm going to change it to 3, and then to an order of 5. We'll do it one more time. Beautiful. Okay. So regardless of whether the order of the zero is 1, 3, or 5, you should see that the sign of the function is changing. Okay. At that x-intercept, the left of it and to the right of it, the signs are opposites. One is negative, one is positive. Now, if the order is odd, for example, if it's 1, you see it's crossing linearly. Okay, I know it's not a straight line, but if you were to zoom in, then it looks like a line. Okay, it's not, but it looks like very much like a line. Now, but if the order of the zero is odd and it's greater than 1, so like 3, 5, 7, 9, what you see instead now is a point of inflection. Okay, so it looks like a cubic is being graphed on that x-intercept. Okay, like it looks like x cubed is graphed on the x-intercept of -3. So remind yourself, if the order of the zero is odd and it's greater than 1, you have to draw a cubic. Now, one thing you'll see in the next example is when you have a graph, you don't really know what the order is. For example, if you look at the x-intercept here, if I didn't show you the equation, can you not argue that the order of the zero could be 2? It could be 4, it could be 6, it could be 8, it could be 10, it could be any even number. But to keep it simple, we are going to assume the least possible degree of the function. So yes, it could be an order of 2, 4, 6, 8, 10, 12, so forth and so on. We are going to assume it's an order of 2. Okay, now if it's a point of inflection, then we're going to assume it's an order of 3, but in the back of our minds, we know it could be 5, it could be 7, it could be 9. Now, if it crosses linearly, then there's no doubt it has to be an order of 1. Okay, so that's what you're going to use, the knowledge of the zeros, to help you graph a polynomial function from factor form. It's a lot quicker than using the interval table. Okay, so hopefully the animation was pretty helpful, but to quickly summarize it, we have this little box here. If the order is odd, you'll see on the graph, as you pass the x-intercept, the function will change signs. Now, whether you pass through linearly or whether you have a point of inflection, that depends on the actual order of the zero. And if the order of the zero is even, you're not going to change signs. You're going to keep the same sign. So positive to positive or negative to negative. And no matter what the order is, if it's even, it will always look like you're bouncing off the x-axis. Okay, let's do a few questions to help us practice. So I have 5 graphs here. I want to state the least possible degree of the polynomial. So I have this graph. So let's look at the x-intercepts and focus on that. So this 0 has an order of 1, order of 1, order of 1. So you have 3 zeros and they all have an order of 1. So guess what? The degree of this polynomial is 3, right? You basically have 3 linear factors if you can imagine the equation. How about this graph? Order 2, order 1. Now wait a minute. For this 0, can we not say it's an order of 4 or 6 or 8 or any even number? But we are since asked to find the least possible degree, then we're going to assume it's 2. Could it be 4? Yeah, maybe, but we're going to go with 2. So 2 plus 1, that means the degree is 3. So these two are actually both cubics. Let's go with this one, least possible degree, so we're going to say it's 2. Order of 2, so that means C is a quartic. Order of 1, okay, this one's obvious, has to be 1. Now this one could be 3, 5, 7, 9, but we're going to assume 3. Okay, least possible degree. Oh, what do you know? That one's quartic too. How about this one? This is order of 3, order of 2. So this one is degree of 5. It's a quintic. Okay, so by looking how the graph is behaving at that x-intercept, you can determine the order of the zero, of all the zeros. And once you know the order of the zeros, then you can come up with the degree of the polynomial. All right, so let's fill in this table. And actually, I wanted to graph the 3 functions for good practice. That's why I left a lot of space at the bottom. So let's fill in the table. So this one's a degree of 3 because there are 3 linear factors. This one of the factors repeated, but if you count them out, you still have 3. This one, ooh, one of them is repeated 3 times. So 3 plus 1, 4. Y-intercept, let's quickly do a calculation. F of 0, G of 0, that's 1, negative 2, that's negative 4. This one is 1, negative 1, negative 1, negative 3 is 3. Okay, and behavior. You know what, before we do end behavior, let's just fill in x-intercepts and leading coefficient. So x-intercepts will be negative 3, negative 2, and 1. This one is 1/3 and negative 2. This one is negative half and 3. Okay, now leading coefficient, you have to do a bit of math to find out, and I wrote down how to find out from factored form. You find the product of all the x coefficients and any number that has been factored out. So the x coefficient here is 3, but since there's 2 of these factors, you write 3 squared, or 3 times 3 times negative 2. Now I didn't say 1 because anything multiplied by 1 is the same thing, so you could say 3 squared times 1 times negative 2. So 3 squared times 1 times negative 2. Let's write it down like this. So that's negative 18 is your leading coefficient. How about this one? So the x coefficient, multiply all the x coefficients and a number factored out. So this is 2 cubed times 1 times negative 1. Which is negative 8. So why did I solve for leading coefficient? Because with the degree and the leading coefficient, I can tell you the end behavior. So this is quadrant 3 to quadrant 1. This one is quadrant 2 to 4. And this one is quadrant 3 to 4. Let's triple check. Negative leading coefficient, even. This one, good. Okay, perfect. Hopefully I didn't make a silly mistake here. So let's do the first one. The first graph is pretty easy. So this is the alternative. This is the other way to graphing a polynomial function from factored form. So instead of using the interval table, let's plot out the x-intercepts and the y-intercepts, and then I have the end behavior, so 3 to 1. Okay, so quadrant 3 to quadrant 1. So then at each x-intercept, all the zeros have an order of 1 here. Okay, look at the factors. Exponent of 1, 1, 1. So my plan is I'm going to cross linearly. So let's do it. Okay, label, and we're done. Okay, next one, -2, 1/3. And I'm not drawing the scale, of course. What's a y-intercept? Y-intercept's -4. Okay. And the end behavior is quadrant 2 to quadrant 4. So just to show myself what my game plan. So in addition to the end behavior, my game plan is I'm going to bounce at 1/3 and cross linearly at -2, because that's what the factors are telling me. The orders of the zeros are telling me. So bounce at 1/3. Ooh, this one's going to be... you know what? I can foresee a problem, so I'm going to just make that a little closer. Okay. Alright, hopefully that helps. Here we go. So cross linearly at -2 and bounce at 1/3. All right, last one. So let's plot the x-intercepts. And the y-intercept is 3. Okay, so what's the end behavior? 3 to 4. What's the game plan? I'm going to do a point of inflection at -½ and then cross linearly at 3. So point of inflection and then cross linearly at 3. Beautiful. Oh, that was nice. Okay, so that's how I graph polynomial functions from factor form. Can you use an interval table? Of course you can, but I really think this way is much more efficient. And by the way, that's how I did this one. I did it really quickly. I didn't use test values. I just imagined the graph in my head. So yeah, you can have fun doing test values though. Yeah, so hopefully you're comfortable using the order of the rows and the end behavior to do the graphs. It just takes, I would say, 5 questions and you'll be pretty good at it.